set this to record to cloud. So today we're going to be talking about, in one aspect of our discussion of stereochemistry, I always like to talk about Fischer projections. So Fischer projections are really wonderful. Sorry about that. There's a little bit of lag in my connection. So a Fischer projection is a method of drawing a compound with multiple chiral centers, such as sugars. So when you think about Fischer projections, you think of Emil Fischer, who did a lot of the seminal work on sugar chemistry. So a Fischer projection is a 2D drawing of a molecule that shows a chiral carbon at the intersection of two lines. So for example, at this intersection point, that intersection point is a carbon. Okay. The horizontal lines, so our horizontal lines represent bonds that project out of the plane of the screen, okay? So everyone notice these horizontal lines? You can think of them like wedges, They're pointing out of the plane of the page. So for example, if we have an OH and a hydrogen on a horizontal line, from our perspective, here's what we see. We have our OH and our hydrogen pointing, are they pointing towards us or away from us? If we're looking at our 3D view of the Fischer projection, are they pointing towards us or away from us? Towards, exactly. So they have a wedge. Now, if we take a look at our vertical lines, the vertical lines represent bonds that project into the plane of the screen, so dashes. So if you take a look for our vertical lines, we have our aldehyde and our alcohol. Is our aldehyde pointing towards us or away from us from this view? Is this aldehyde up here pointing towards or away from us? Away, exactly right. Exactly right. So just a visualization once again, here are the three depictions: model, dash wedge, and Fischer projection drawings. Now, there's an important rule for Fischer projections that you really need to focus on. The most oxidized carbon, which for sugars is usually the aldehyde or ketone, is always at the top. So in this case, our aldehyde is always drawn at the top of our structure. So it's always at the first carbon or first position. Does that make sense? Does everyone notice how this aldehyde is at the top? Now this is important because if you draw your Fischer projections upside down, it creates issues for this model. So you always put the aldehyde or ketone group on the top, the most oxidized carbon. Okay, so let's take a look. Let's take a look now and let's deal with the following structure. So we're asked to indicate the configuration of each stereocenter. So our horizontal lines, we're going to draw them as wedges. So I know that I need to convert all my horizontal lines into wedges. Remember how we discussed that earlier? Our vertical lines, we convert into dashes. So these are going into the plane of the page. Okay, so here's our model picture of this structure. Now, if we want to assign the configuration, where do we need this hydrogen to be? Do we need it to be out of the plane of the page or into the plane of the page? Do you need it to be towards us or away from us? Where do we need this? We need the hydrogen to be away from us. So I'm going to turn this molecule. I'm going to turn my molecule. Now is my hydrogen away from us. Now is my hydrogen away from us. If I've turned my molecule as so. Can you see the hydrogen anymore in the front? Can you see the hydrogen anymore in the front? Yes or no? You cannot. Exactly. The hydrogen's away from us. Now we're just going to draw what we see. We're now just going to draw what we see. Okay, so we're going to draw what we see. Okay, so from our model, we have our alcohol on top, we have our aldehyde on the right-hand side, and then we have, so looking at this alcohol fragment right here, is this alcohol fragment pointing out of the plane of the page or into the plane of the page? Is it pointing towards us or away from us? This CH2OH, is it pointing towards us or away from us? This one right here? This one? The CH2OH? Let me show you the perspective. So the hydrogen's in the back. So let's look at it from this perspective now. Is this CH2OH pointing towards or away from us? Towards, exactly. So we're going to give this CH2OH a wedge. And of course, our hydrogen gets a dash. Okay, now all we have to do is assign our priority numbers. So what is our highest priority group in this molecule? So A, B, C. What's our highest priority group? A, B, or C? This is the same process that we used for assigning R and S configurations. So let's compare. So on A, directly attached on A, we have an oxygen. For B, we have a carbon. And for C, we have a carbon. So what wins out? Oxygen or carbon? What wins out? Oxygen, right? So we're going to put A as number 1. Okay, now let's compare B and C. So attached to each of these carbons, B and C. So on B, we have an oxygen, and a carbon. For C, we have an oxygen, a carbon, and a hydrogen. So which group wins out, B or C? Which one wins out? B, exactly right. Just as a reminder, remember that aldehydes, if we have a carbon-oxygen double bond, it's treated as 2 single bonds. Remember that rule? That double bonds are treated as 2 single bonds? So now that we have our priority groups established, we trace from highest to lowest priority. And as we see, we're moving clockwise. So we assign the center as an R configuration. Does that make sense to everyone? Does that make sense? Is everyone comfortable with this idea? Does this look familiar? The only thing that's new is going from this dash wedge Fischer projection using your model to put the hydrogen in the back. Once you have the lowest priority group in the back, it's exactly the same as always. Now, I just want us to take a note really quickly that if the OH is on the right-hand side, in this case, we observed an R configuration. This is not always the case, but it's a general trend that we see in many of our Fischer projections. What I would always recommend is that you do this kind of configuration assignment from scratch, just like we did together. Now, what I want you to do now is I'd like you to indicate the configuration of each stereocenter in the following compound. So take a look at this compound, try making a model. I'll be making a model for you as well. And then we'll come together to discuss in a few minutes. And we'll assign the configuration at that center. Exactly right, exactly right. So just as a refresher, just as a continuation, so from our Fischer projection, we established our OH and hydrogen are pointing out of the page, our aldehyde and our methylene group are pointing into the page. We then carefully rotate our molecule. We carefully rotate our molecule to put the hydrogen in the back. And then we draw what we see. And that's it. The only tricky part is rotating the molecule. And that's why I like you to play with a model kit. So that way you can get used to the idea of rotating molecules and changing your perspective in 3D space. Does that help, Christine? Does that make a little bit of sense? Perfect. So I'd like you to try out this process on the following structure. And I'll be making a model for you so we can check our work. Yeah, this class has been quite fun in terms of the idea of enantiomers, because the camera flips any structure I make. So I've been having to make a lot of the enantiomers of the structures that we've drawn to make sure the camera shows them properly. So let's take a few minutes, and you're more than welcome to message me via the Zoom chat, whether it's R or S. Okay? Wow, some people are really fast at this. Let's give everyone about another minute and a half, and then we'll come together as a group to discuss. And if you take a biology class in the future, this skill you'll see again. So this even shows up in biochemistry as well. Okay, let's take about another minute, and I'm already seeing a lot of reasonable responses. Okay, so let's take a look at the following structure. So I'd like you to jog my memory. The horizontal lines, these horizontal lines, do I draw them with wedges or dashes? These horizontal lines, do I draw them with wedges or dashes? Wedges, they're going out of the plane of the page. Exactly right. Okay, and my vertical lines, do I draw them with wedges or dashes? Dashes, exactly right. Okay, now remembering our rule for Fischer projections in general, and this is just something to avoid drawing a Fischer projection that catches people off guard, we put our most oxidized carbon on top. So we've checked all the boxes, okay? Now I'm going to show you a model of the structure, okay? So our OH and hydrogen are pointing out. The OH is on the left-hand side. And now what we're going to do is we're going to rotate our molecule. We're going to rotate our molecule so that our hydrogen's in the back. So I'm going to rotate my molecule so my hydrogen's in the back. And now what I'm going to do is I'm just going to draw what I see. So I'm going to draw what I see. So my methylene group is on top, my alcohol's on the right, and my ethyl group's on the left, and my hydrogen's in the back. Okay, perfect. So now that we have our drawing with the hydrogen in the back, we now have to assign priority. So let's repeat this process. So A, B, C. What is priority 1? What's the highest priority group? A, yep. What is the second highest priority group? Yep. And what's the third highest priority group? Okay, so if we trace from highest to lowest priority, we see that it's counterclockwise. So this center is an S. Okay, let's just take a note that this OH was on the left-hand side. It's not always a general trend, but it can help us guide our first hunch guesses. Okay, that was really good. Everyone did quite a good job with this problem. So the beautiful thing about Fischer projections, and the reason why it's really nice for sugars, is Fischer projections readily show if two compounds are enantiomers or diastereoisomers. What do you mean by why did we not flip? So we started off with the view like so from our Fischer projection, and then we rotated our molecule so the hydrogen was in the back. Would you mind elaborating on the question, why did we not flip the molecule? Ah, okay, perfect. No problem, I just wanted to check. Okay, so now the beauty of, it's the most oxidized carbon. So if we compare this carbon to this carbon, this one is more oxidized. It's the most oxidized. So it's the most oxidized carbon. Perfect. Okay, so the beauty of Fischer projections is they really help you see enantiomers and diastereomers unambiguously. The location of the substituent, whether it's on the left or the right, determines the stereochemistry of that chiral center. If two compounds have a substituent at different positions, left or right, on a chiral center in a Fischer projection, the stereocenter has the opposite configuration. So do you notice how if we change the position, we have flipped our stereocenter? So as a result, what would this pair of compounds, would they be enantiomers or diastereoisomers? Have we flipped all of our stereocenters or just one? What do we call that when we flip a few of our stereocenters? Do we call, yep, exactly right, diastereoisomers. Likewise, likewise, we can also consider flipping our bottom stereocenter and make another set of diastereoisomers. And if we happen to flip both of our stereocenters, if we compare these two compounds, we flipped both of our stereocenters, so we call these compounds enantiomers. So Fischer projections make the whole idea of diastereomers and enantiomers really easy to see. That's why I like them. Does that make sense, everyone? The location of your substituent, left or right, determines the relative stereochemistry. And as a result, if a substituent changes in position, then we are flipping that stereocenter. Okay, so just to showcase some configurational analysis, I'm going to make a model of each of these structures. So let's start with our first structure right here. And let's make a model together of the following structure. I really want you to be able to visualize structures using your model kit. It's an invaluable tool, and most importantly, it's one of those things that once you practice enough with your model kit, you're going to be able to do this without a model kit, just staring at the molecule. And that's when I think this skill really begins to pay dividends. Okay, So let's take a look at the following structure. So we've already converted this structure to dash wedge notation, reading our Fischer projection. So here is our structure. Whoops, let me switch this position really quickly. Okay, here we go. So we have our ethyl group on top. We have our methyl group pointing away. And we have both of our bromine groups pointing out of the page on the right-hand side, right? So we've effectively made a model of this structure. Okay, now let's look at our topmost stereocenter. And if we need to assign the configuration of our topmost stereocenter, do we need our hydrogen in the front or in the back? Do we need our hydrogen in the front or in the back? This one right here. Oh, is the camera making a mirror image for you? Ah. Okay. We'll perform the analysis for this, and then once we get to our drawings, I'll draw what I see from my view. Okay, so do we need our hydrogen to be in the front or in the back? Back. Okay, so we're going to tilt this first carbon and we're going to move it so our hydrogen's in the back. Okay? And now all we have to do now that our hydrogen is in the back, all we have to do is draw what we see. All we have to do is draw what we see. Now, I'm going to rotate our perspective a little bit to make this slightly easier on us. And from that, we see that our ethyl group is on top. Our bromine is going out of the page. So from this perspective, and our methylene group, or in this case, our ethyl group, since it has 2 carbons, is on the right-hand side. Okay, now that we have everything set up, let's take a look at just this first carbon that we've manipulated, and let's assign R versus S. So in terms of priority, let's look at this first group and let's assign A, B, and C. So which group on this first carbon is priority 1? Which group is priority 1 on our first carbon? A, B, or C? Yep, B gets number 1. What's our next highest priority? What's our next highest priority? C, yep. And what's our lowest in priority group? A. Okay, so if we draw an arrow going from B to A, we see that it's counterclockwise, so we'd assign the center as S. Okay, let's now return to our model. Let's return to our model, and I'm going to return it to our Fischer projection view. And now let's just look at our bottom stereocenter now. Let's look at the bottom stereocenter on our second carbon. So where do we need our hydrogen? Do we need it in the front or in the back? Where do we want this hydrogen to be? In the back. So we're going to rotate our carbon-carbon bond. So now our hydrogen is in the back. And I'm going to shift the view a little bit so that way we match our model kit with our structure drawn. So in this case, we have our methyl on top. Yep. We have our bromine on the right, and we have our alkyl chain on the left. Now, all we have to do is repeat this process of assigning priority. So let's assign priority now. So what's the highest priority? A, B, or C? Which group gets the highest priority? A, B, or C? A, yep, so we'll put A as number 1. What's the next highest priority? B, yep. And what's the lowest in priority? Yep. So if we draw an arrow going from highest to lowest priority, we see it's clockwise, and that stereocenter is R. Now, one thing I want you to appreciate is that the bromines are both on the right-hand side, but we have different configurations, okay? So don't just say right is R, okay? You really have to go step by step, rotating your model kits, and then checking using our methods for assigning configuration. Does this example make sense to everyone? Is everyone comfortable with rotating Fischer projections? Is everyone okay so far? When you used your own model kit, did you get similar results? If we flip the molecule vertically, let's take a look at that idea. Let's entertain that idea. What do you mean by flipped vertically? You mean if we just turn the molecule around like this and then we drew what we saw? That would also work. There's no reason why it wouldn't. As long as your hydrogens end up in the back, then you can assign R and S. Yep. Now, and here's the cool part. Here's the cool part. And this is the part that, this is the reason why I like Fischer projections so much, because they save us so much time. Okay, if we compare these two structures, and we know initially we have assignments of S and R. If I flip my first stereocenter, if I change the relative position of my bromine, a priori, without doing any rotation, what will happen to the configuration at this top center? Will it be S or R if we change the position of the bromine? What will the configuration be at this first carbon? Will it now be R or S? R, exactly right. If we change the relative position of our substituents in a Fischer projection, the configuration of our stereocenter will flip. So to showcase that, we're going to take our top bromine and we're going to switch its position. Okay, now, just as an exercise to prove to ourselves that this center, in fact, is now R, we're going to rotate our model kit. We're going to rotate our model kit so the hydrogen is in the back. And then we're going to draw what we see. So we have our bromine on top, our ethyl group pointing out of the plane of the page, and our alkyl bromide on the right-hand side. Now, just like before, we're going to assign priority. We're going to assign priority. So if we look at A, B, and C, what's our highest priority group? A, yep. Followed by B, followed by C. So if we draw an arrow going from highest to lowest priority, do we have an R or S configuration at our first center? Is that R or S? R. Okay, so you don't just have to take what I say at face value. We have the tools to analyze and assess what I'm saying. So we clearly see it that if you've changed the relative position of substituents in a Fischer projection, the stereocenters will flip in assignment from S to R or from R to S. Does that idea make sense to everyone? When we manipulate the models, does everyone clearly see how the center changes in configuration when you change the bromine's position? Okay, perfect, perfect. So let's now tackle some more Fischer projections. I really want you to be prepared for your biochemistry classes. So what I want you to do is to indicate the configuration at each chiral center for the following pair of molecules. And I'd like you to tell me, are the following compounds enantiomers or diastereoisomers? And I'm sure you can answer the second question faster than you can answer the first. So I'm going to call this center 1 and 2, center 1 and 2. And I really recommend when you're doing your assignments, just focus on one of the molecules at first glance and then handle the second one later. So you're welcome to, for this structure, which I'll call A, you're welcome to message me in the chat whether you think center 1 is R or S or center 2 is R or S. And then I'd like you to tell me whether the pair of compounds are enantiomers or diastereoisomers. So let's take a moment to work on that. I'll make a model for everyone, and then we'll come together to discuss in about 3 to 4 minutes. And don't be shy to message me questions using the chat function. Ah, okay. Let me. I'm just going to do a quick, I just want everyone to give me some quick feedback. So what are you currently seeing? Do you see this chlorine on the left or right hand side? The left hand side. Okay. Okay, perfect. Okay, so let's get a few more responses for each of our stereocenters, and a few more responses whether we see enantiomers or diastereoisomers. So we'll take about 2 more minutes on this topic. Okay, my check that the cameras are working. Sorry for any confusion about that. It's good that we got that taken care of. So I see a lot of reasonable responses so far. So let's go through and let's start our analysis. So first and foremost, we have our chlorine on the right-hand side, and our oxygen is on the right-hand side, and both of them are pointing out of the plane of the page. What we're now going to do is we're going to rotate each of our carbons so our hydrogens are in the back. So I'm going to rotate each of my carbons so my hydrogens are in the back. And now all I'm going to do is I'm going to draw what I see. Okay. So I have my methyl group on the right-hand side, my chlorine on the left, my alcohol on the left-hand side, and my other methyl group on the right-hand side, and both of the hydrogens are in the back. Okay, that's what we've established so far from our view. Does everyone see that? Does this drawing match the figure that we are looking at currently? Is everyone okay with what we've drawn so far? Okay, perfect. So now let's assign priority. So starting off with our, so this first figure, so this is A, we're going to assign priority. Our chlorine gets priority 1, this carbon with the alcohol gets priority 2, and our methyl group gets priority 3. If we trace from highest to lowest priority, is this an R or S configuration if we're going counterclockwise? What do we assign stereocenter 1 as? S. Exactly right. Now let's repeat this process for stereocenter number 2. So our alcohol gets highest priority, then our carbon, then our methyl group. We trace from highest to lowest priority. If we're going clockwise, is stereocenter number 2 going to be R or S? If it's clockwise, what do we call that? R, exactly right. So we have our assignments of S and R for structure A. Now, without doing any further calculations, if we change our chlorine's position, what happens in structure B? What is the stereocenter assignment for carbon 1 going to be now? We go from S to what? R, exactly right. Likewise, if we flip the position of our alcohol, what happens to stereocenter 2? What's the configuration of stereocenter 2 going to be now? It goes from R to what? S, exactly right. Now, let's prove that to ourselves. Let's not take out anything at face value here. Let's prove that to ourselves. So I'm going to make a model for you. Okay, so here is structure B. Does everyone agree that our chlorine and alcohol are now on the left-hand side? Does everyone agree that our chlorine and alcohol are now on the left-hand side? Okay, wonderful. Now, what we're going to do is we're going to rotate each of our carbons so this hydrogen is in the back. Okay, so now both of our hydrogens are in the back. So we're going to draw what we see for structure B. That's all we have to do, just drawing what we see. Give me one moment to refocus our view. Okay, so here is structure B. So we have our chlorine on the right, our methyl group on the left. On the bottom, we have our methyl group on the left and our alcohol on the right, and both of our hydrogens are in the back. Okay, let's now assign priority. It doesn't matter what substituents you flip. If you change the relative position of any substituents, the configuration will flip, as long as those substituents are attached to the same carbon. Yeah. Assigning priority, our chlorine gets priority 1. Our carbon attached to the alcohol is priority 2, and our methyl group is priority 3. So as we look to see, is our arrow moving clockwise or counterclockwise for carbon 1? Is carbon 1 R or S? Clockwise, ergo it's R. Okay, for carbon number 2, assigning priority, we have 1, 2, 3. We draw our arrow from highest to lowest priority. And are we going clockwise or counterclockwise? Is that an R or S center? S, exactly right. Perfect. So we've assigned our configuration correctly for each of our stereocenters. And now my question to all of you is, since the configuration of all of our stereocenters is flipped, what do we call it when all of our stereocenters have the opposite configurations? What do we call it when we have mirror images? Are these enantiomers or diastereoisomers? Enantiomers, exactly right. Okay, wonderful. Is everyone comfortable with this example now? Okay, perfect. So let's bring up and let's, whoops, one moment. Sorry about that. Let's talk a little bit about chirality at nitrogen, phosphorus, and sulfur. So nitrogen readily inverts at room temperature. So nitrogen does not form a chiral center. No. The assignment is unique for each molecule, and it really depends on the relative position of the substituents. You could have, for example, RR or SS. For example, this molecule is SS. While this molecule is RR. So it really does depend on the relative position of your substituents. Yep. Okay, so thankfully, because nitrogen readily interconverts at room temperature, we don't have to worry about chirality at nitrogen. It readily undergoes a flip in its trigonal pyramidal geometry. So it readily inverts its lone pair. Now, nitrogen's larger, bulkier cousin, phosphorus, inverts more slowly. So chirality at phosphorus can be observed, and we can even isolate enantiomers. So just as a side note, the lone pair is the lowest priority group for a configuration assignment. It's even lower than hydrogen. So if we think about the following compound, this would be R-methylpropylphenylphosphine, and it's configurationally stable. It doesn't interconvert. Don't worry too much about assigning R and S for phosphorus. Phosphorus-based ligands are very useful for chiral catalysis, and you'll see them in upper division organic courses. So chirality can exist at non-carbon atoms. That's the main takeaway. Now, more interestingly is this idea of prochirality. So what is prochirality? It's a molecule that is achiral but can become chiral by a single alteration. For example, addition of a hydrogen atom to an asymmetrical ketone results in a chiral compound. How many substituents does this new carbon atom have? How many substituents do we see? How many unique substituents? 4. Ergo, this is a chiral carbon. So we'd say that 2-butanone is prochiral because, quote unquote, it can become a chiral center. Does that make sense to everyone? A prochiral compound is a compound that can become chiral with the addition of a functional group or atom. So for example, ethanol, we call this a prochirality center because if we replace the hydrogen with something else, we would generate a chiral center. So a prochiral carbon or a prochirality center is a center that with one modification can become a chiral center. Okay. Now, we can take this idea of prochiral distinctions a bit farther. So in terms of faces, an sp2 carbon with two groups that are the same is a prochirality center. Oh, sorry, this is sp3. Sorry, an sp3 carbon with two groups that are the same is a prochirality center. The two identical groups are distinguished by arbitrarily assigning one hydrogen as higher priority than the other. So, for example, let's suppose we have these two hydrogens. If the center becomes R, if that hydrogen is designated as higher priority, then that hydrogen is pro-R. So let's suppose we assign priority. So 1, 2, 3, okay? And that in turn gives us an R configuration. Then we'd call this hydrogen in green pro-R. Does that make sense to everyone? Okay. So we assign this one as higher priority than the other. We do our typical priority assignment. We see a clockwise rotation. So this would be a pro-R hydrogen. Likewise, if the center becomes S, if that hydrogen is designated as higher priority, the hydrogen is pro-S. So let's suppose for a moment that we designate this hydrogen in the back as higher priority. So this hydrogen in the back is higher priority. So if we rotate our molecule, to put this hydrogen in the back. So let's look at a picture of this. Okay, so let's look at a picture of this. Okay, so we have our alcohol on the right, our methyl on the left. Okay, we have our hydrogen in the back, and in blue, I'm going to put my pro-S hydrogen. So let's see. Whoops, I have it in the wrong spot. One moment. Okay, so let's pretend, so we've established that this hydrogen is pro-R, because if we put the other hydrogen in the back, we get an R configuration. Now let's look at our blue hydrogen. So this blue hydrogen. So for our blue hydrogen, we're going to assign it as the higher priority group. So we're going to try to put this other hydrogen in the back. So we're going to rotate our molecule. To put the non-blue hydrogen in the back. And now, once we have our priority groups established, we're just going to draw what we see after rotation. So after rotation, we have our pro-S hydrogen in front. We have our methyl group up top. We have our OH on the right, and our other hydrogens in the back. Now, given this arrangement, let's now assign our priority groups. Let's assign our priority ranking. The alcohol is priority 1, the methyl is priority 2, and this pro-S hydrogen is priority 3. If we count from highest to lowest priority, what is the configuration at this center? Is it R or S? Are we going clockwise or counterclockwise? counterclockwise. So this would be an S center. So we'd call this hydrogen Pro-S, because designating this hydrogen as higher priority results in an S configuration at our center. Does that make sense? Does that clear things up? So we're designating one of our hydrogens as arbitrarily higher priority. We then look and see if one of our hydrogens is higher priority, what is the configuration at our center? If it's R, that hydrogen is pro-R. If it's S, the hydrogen is pro-S. So for example, looking at our model, if we assigned this green hydrogen as pro-R, so if we assign this green hydrogen as higher priority, so 1, 2, 3, 4, all we have to do now is check and see whether going from highest to lowest priority, we have an R or an S center. And as we can clearly see, our substituents, if we count from highest to lowest priority, we're counting in a clockwise direction, so this center is R. Let's suppose we designate our blue hydrogen. Whoops, one moment. So let's suppose that we designate our blue hydrogen as higher priority. So we have the following priority ranking. And if we rotate our molecule, so this hydrogen is no longer in the back, and our lower priority hydrogen instead is in the back, we get the following arrangement. So as we can see, if we count from highest to lowest priority, we're counting counterclockwise, we'd get an S stereocenter, so we call this hydrogen Pro-S. Is everyone comfortable with this idea of pro-chirality? Does anyone have any questions on this section?
Martinez, I have a question.
Sure, yes.
So if you have two hydrogens, so you just pick one of them to be the higher priority?
Yes, it's perfectly arbitrary. The only thing that you're noting is whether when that hydrogen is designated as higher priority, is that center now R or S? Okay.
And then the other hydrogen that was a lower priority than the previous one, how would you determine the configuration for that? Because I know.
So the way I like to think about it is we pick one of our hydrogens and we replace it with a group X that is priority number 3. Okay. And then I just look at this new molecule and I ask myself, is that center R or S? And I just repeat this process for both of my hydrogens, and I just ask myself once again, is this new molecule with X going to be R or S?
All right, I got it.
Okay, perfect.
Yeah.
Okay, so there's one other aspect of prochirality, and this is concerned with planar carbons. So planar faces can become tetrahedral after addition, are different from the top or bottom. So there are 2 different faces, and which lead to different tetrahedral centers. A center at a planar face at a carbon atom is designated as Re if the 3 groups in priority sequence are clockwise, or as Psi if they are counterclockwise. So let's talk a little bit about what that means. So let me color code this. So if we think about the Re versus Psi faces, and we think about our priority groups, so let's look at an example of an addition. So the top face would be our re face, and the bottom face is the psi face in this case. Now, we're going to look at our three groups in terms of priority, and as we notice, from our top face, from the re face, going from highest to lowest priority, our groups are clockwise in our planar carbon. Does that make sense to everyone? Does everyone see how from the re face, our groups ranked in order of priority are clockwise? Now let's look at the psi face view. Let's look at the psi face view. And to do that, I know I've been saying this a lot, we're gonna build a model. We're gonna build a model to help everyone see what's going on. So give me one moment. I'm almost done putting together the model. Okay, so here is the sorry. Okay. One quick fix. It's hard getting used to the camera showing me a mirror image now. Okay, so perfect. So let's suppose we're approaching from the re face, okay? So this is the re face approach. This is our current view. So we're approaching, we're looking at it from the perspective of the re face, and we can see that our substituents are clockwise in order of priority. Now, for the psi face, we're going to attack from the opposite side. So I'm going to flip my molecule over, and I'm going to show you the attack from the psi face. So we're now viewing our molecule so that our eyes are attacking from the psi face. And I'd like you to tell me, let's just draw what we see. So from our perspective, from our attack from the psi face, we have our carboxylic acid. We have our other carboxylate group, and we have our hydrogen. Okay, so this is our view from the psi face. Does everyone see what I'm seeing? So this is our view. We're attacking from the psi face. Now, given our priority numbering that we assigned our hydrogen as 3, this carboxylate as 1, and this other carbon as 2, if we look at our substituents, arranged in order of priority, are they clockwise or counterclockwise? Are they clockwise or counterclockwise? So counting from highest to lowest priority, it's counterclockwise. So we designate this face as the psi face. Does that make sense to everyone? Is everyone comfortable with this idea? Okay. Okay. Now our last major topic that we're going to broach and address is this idea of separating enantiomers. So enantiomers have identical physical properties, so they cannot be easily separated. It's an unfortunate trait. This was primarily, if we're looking at, for example, racemic lactic acid, both of these two enantiomers have identical physical properties. However, we know that diastereomers have different physical properties and can be separated via physical separations. Okay? So we can use a chiral resolving agent to convert our enantiomer into a set of diastereomeric salts. So in this first case, we just have a mixture of enantiomeric salts, and these cannot be separated. However, if we change our resolving agent, and instead we use a chiral resolving agent, now, because our resolving agent is chiral, the salts that we generate, so for example, if we have a center we have the R and S enantiomer, when we generate our salt, we have a mixture of an RR salt and an RS salt. And as we notice, because the configuration of one of our centers is different, but the configuration of all of our centers are not different, these are diastereomers, and these can be separated. Okay, so the reason why we use a chiral salt is because we can separate the diastereomeric salt complex formed from each of our enantiomers. Does that make sense? Does that make sense to everyone? This idea of chiral resolution? We can separate diastereomers, so we convert our enantiomers into a mixture of diastereomers. Okay, so that's just a nice little subnote on how enantiomers are practically separated. And for example, one of these salts may crystallize out, while the other remains in solution. So you can selectively crystallize out one of the enantiomers, or you can separate them via solubility, polarity, you can separate them via chromatography. The world really is your oyster once you have a mixture of diastereomers. Now, in terms of alternate methods, one method, yes, this classic example was in Pasteur's study of tartaric acid. So the salt doesn't flip a stereocenter, it just makes it so you now have a pair of stereocenters where they only differ in configuration at one of your centers. So instead of being enantiomeric salts, these two salts are diastereomeric, and we can separate diastereoisomers readily. Yep. So one of the other methods that's been sort of expanding in popularity for very small scale determination of enantiomeric purity in percent EE is chiral column chromatography. So a chiral column contains chiral molecules as part of their stationary phase column coding. So you have this chiral molecule coding. And as enantiomers have different interactions with the chiral column stationary phase, the enantiomers will progress through the column at different rates and exit the columns at different retention times. So this allows a mixture of enantiomers to be separated. This is not as popular for large scale purifications, but if you're reading through the literature, you may see a chiral column trace where they calculate EE using chiral column chromatography. It essentially utilizes the same lock and key principle where enantiomers interact differently with chiral molecules. So we can separate enantiomers using this difference in interaction. Just exposing you to a few different techniques that are used for purification of enantiomers. Now, as our last topic for this session, we're going to talk about the stereochemistry of alkenes. How do we assign the configuration of alkene stereocenters? So we have our good old friends cis and trans. So cis, the substituents are on the same side of the alkene. Trans, the substituents are on opposite sides. So this would be cis 1,2-dichloroethane. Well, this would be trans 1,2, oh, sorry. Dichloroethylene. So we have cis versus trans stereoisomers. However, in cases where there are multiple substituents on the alkene, we're going to need to utilize the IUPAC convention of Z and E assignments. So in terms of Z and E assignments for alkene stereocenters, what you're going to do is you're going to rank each group on each side of the alkene in order of priority. So if the highest priority groups are on the same side of the alkene is Z. If the highest priority groups are on opposite sides of the alkene, we have an E configuration. So let's look at an example. So in this case, we have multiple substituents. So when we say cis or trans, what are we talking about? Cis or trans is ambiguous. However, if we use priority groups and Z and E conventions, it becomes quickly apparent what groups we're referring to. So on the right-hand side, our ether is higher priority than our hydrogen. On the left-hand side, our fluorine is higher priority than our ethyl group. Now, my question to all of you is, are our highest priority groups on the same or opposite sides of the alkene? Are our highest priority groups on the same side of the alkene? Are they both on the bottom side of the alkene? Same side, so we call this Z. Now comparatively, in this case, we have our same priority assignments. And now, are our high priority groups on the same or opposite sides? Are they on the same or opposite sides in the structure on the right? Opposite. So we call this an E alkene. Okay. Let's do some practice on this now. Let's do some practice. So let's take a moment and I'd like you to assign the configuration of the following alkene. So this is just a study in assigning priority. So let's focus on developing that skill. And then we'll give everyone about 2 to 3 minutes to work on this, and then we'll come together as a group to discuss. And if you are willing to contribute to the class discussion, don't be shy to type in the chat whether you think the center is Z or E. And we'll discuss in about a minute and a half. So we already see some answers being proposed. Let's get a few more before we discuss, just so that we have a nice pool. And it's always interesting when we have disagreeing answers. Those are always but it looks like the class is in pretty strong consensus. So let's talk about this. So if we compare our centers on the left-hand side, we can clearly agree the center with the alcohol attached is priority 1, or center with the carbon attached is priority 2. Now let's trace through each of our carbons. So this first carbon is a tie. Looking at our second carbon, we can view our olefin as if we had another carbon bonded to it. So in terms of our list attached to this carbon right here, we have 3 carbons and a hydrogen. If we compare to this carbon up here, we have 2 carbons and 2 hydrogens. So this bottom group wins out and gets priority 1. The top group gets priority 2. So as we can see, are high priority groups on the same or opposite sides? Are they on the same or opposite sides? So they're on opposite sides. Ergo, we call this an E stereoisomer. Very, very good. Everyone did a great job answering that question. So let's do another one. Let's do another one. So let's take a moment and let's work on this second compound. So the center is the bond. Yes, it's this carbon-carbon double bond. It just like we have cis or trans stereoisomers with different shapes, the Z and E stereoisomers have different shapes. And it's describing the relative position of our substituents on our carbon-carbon double bond. Yep. So let's take about 1 to 2 minutes to work on the following problem and assign this center as Z or E. And don't be shy to type in chat your response for whether the center is Z or E. Okay, so let's discuss. So obviously our hydrogen's priority 2. This group is priority 1. Now if we compare at our carbon attached, so looking at this carbon on top, we have a carbon, a carbon, a carbon, and a hydrogen. On the bottom, we have a carbon, and 2 hydrogens. So which group wins out? Which group wins out? This top carbon substituent or the bottom carbon substituent? Which group wins out? Top or bottom? Top. So my question to all of you, are our high priority groups on the same or opposite side? Opposite. So do we call this Z or E? Do we call this Z or E? E. So just be really careful with your priority assignments. Let's do 1 to 2 more. It's always good to get practice with priority assignments because alkenes are often it's often a very close debate. So let's look at the following alkene and let's assign it as Z or E. So take a look at this molecule and spend a few minutes, and don't be shy to propose your answer. The main thing is, as long as we have a discussion going, we can talk about it and we can entertain all of the possibilities. So don't be shy to type in Z or E once you've assigned the configuration for the following center. I see a lot of people typing Z, so let's talk about this. Obviously the chlorine's priority 1. So tracing off, this carbon has an oxygen attached. Oxygen, a carbon, and 2 hydrogens. This center has 3 carbons and a hydrogen. Oxygen wins, so this top group is priority 1. Both of our high priority groups are on the same side. So you guys are all perfectly correct in saying that it's Z. Yep. Almost a huge chunk of the class and everyone who responded got that perfectly correct. Very good. Let's do one more before we close out today's session. So let's look at this center and let's assign it as Z or E. Everyone's getting much faster at this. Yes. So we'll do that. We'll rediscuss the previous example right after this one. Yeah, but I'm more than happy to go over that one more time. I see a lot of people typing Z. So let's talk about this. Chlorine is our highest priority. The methyl group beats out hydrogen. These groups are on the same face. So it's a Z olefin. Exactly right. Wow, everyone's super fast at this. Let's look at the previous example that we discussed. And Brandon, is it this one that you wanted to talk about? The one that I put the star next to? Okay, perfect. So in terms of priority, as we recall, so you trace carbon by carbon. Okay, so if we compare our first carbon out, so we're comparing these two carbons, this top carbon has 3 carbons and a hydrogen attached. This bottom carbon has 2 carbons and 2 hydrogens. So the top carbon's priority 1. Hydrogen by default is priority 2, so this bottom group is priority 1. Since both of our high priority groups are on opposite sides, this is the E olefin. Does that make sense? So like in terms of, so we look at the first carbon out. So these are both the first carbon out. So if we're thinking about priority, we look at all the carbons attached to that first carbon and all the groups attached, and we make a list. So in this case, we have 1, 2, 3 carbons attached. In the bottom case, we have 1, 2 carbons attached. And since we have carbon outranking a hydrogen attached, this top group gets priority 1. Oh, perfect. Well, that's it for this chapter. Next chapter, we're going to focus on organic reactions and understanding mechanisms in a logical fashion. We'll be continuing. Yes, sorry about that. Yep, so here's the last one that we covered before that review, which we assigned as the Z olefin. So that's the end of today's lecture. I'm just